Hi, everybody. I chose this music because it was appropriate for what I saw when I looked out the window today. Like, apparently this is our version of a hurricane? Like, we obviously don't get hurricanes up here in the Pacific Northwest, but, um, I guess on occasion, if the conditions work out correctly, we can get what's known as a bomb cyclone, which is just a cyclone and a hurricane are basically the same thing, but it forms very, very suddenly and then dumps lots of rain and wind in this area. So I'm from California, so I'm checking the weather for back home, and San Francisco got 5 inches of rain, which is unheard of. I can't imagine what would happen if Seattle got 5 inches of rain. All at once, I mean. Like, we get 5 inches of rain maybe over the course of the year, of course, but um, this has been my weather update because if I could do it all over again, I'd be a meteorologist. Who is excited for Halloween? I am. I'm going to probably the first like get together slash party that I've been to in maybe 2 years because everybody there I know will be vaccinated, which is wonderful. So I hope you have a good Halloween weekend. The exam's out of the way, so celebrate by treating yourself to some treats. May I recommend? I mean, the ubiquitous peanut butter cups or whatever. Am I gonna dress up? I mean, I'm gonna wear something nice, but I don't know if I would call it a costume. I was going to go with a few friends who were coming up from Colorado, but they have since canceled because they couldn't get plane tickets cheaply, which is a shame. Um, so I'm just gonna go by myself. It's to a coworker's party. Um, and yeah, I mean, I'm just looking forward to seeing actual people besides the two people that I have seen for the last year and a half. One is said coworker who's hosting the party, and the other is another coworker who worked at Edmunds for a while. This is why I know so much about Edmunds. Um, so hi, hope everybody had a good weekend once the exam was done. I have graded your exams. And well, to be more accurate, Canvas has graded your exams, and your scores have been imported to the gradebook. You should be able to see them. If you can't see them, one of two things has gone on. Number one, you may have clicked on the event, I'll call it, that said exam number 1, units 1 through 8. That event is just going to remain in the state that it is. You can ignore it forever. There should be another event that says exam number 1 grade. And this is in your assignments page or your quizzes page or your grades page. Any of those, I think, lead to this. And it will show you your score on the exam. That's out of 75. Now, if you remember that when you were taking the exam, there were 83 points available. And so I had to do this sort of roundabout way, which is where I hide your actual exam score and then I import it into a new exam score. Because Canvas would put it out at 83, because that's what it's out of in the quiz engine. And then you wouldn't have any extra credit. It would all just be credit points. And I don't want that. So I have 10% extra points available on any exam or final, which you can read about in the syllabus, of course. I know nobody reads the syllabus. I hope that someday a student will be like, oh, that's in the syllabus. Actually, if you just say that in response to any question, odds are you're right. Is the test curved? No, not really. So like if you got 90% of the problems right, you actually got a score over 100% just based on how that works. Because there are 8 more points available. So if you scored higher than 75, you got over 100%. I don't curve your scores because what would have actually happened if I curved your score is that everybody's score would have decreased by 8 because the class average was 80%. That's another thing I want to mention. If you were looking at the score averages in Canvas, they're reported incorrectly because Canvas looks at all of your attempts. I only grade the better of your 2 attempts, remember? So I only use the better attempts as the average because that makes more sense. Why would I include all the scores that were discarded? I mean, you might have taken the first attempt and only gotten 30% because the power went out or something. So that's not a valid data point. So I ignore all of the first attempts or the lower attempts. If you only took one attempt, that was your score, it was recorded. Do I release answers for the exams? No. No. You do not get your exam results back. You only get a score. Think of it like the SAT. Why does the SAT only give you your score and you don't get to see what you got right or wrong? Like, you don't get to see the answers. You just see a number and then correct or incorrect. You don't get to study from the SAT, right? That's because the purpose is not for you to review the SAT to see what you missed. The purpose is to assess your ability and mastery of the content. In my class, your exam is strictly a tool for me. I look at your exam and I say, okay, this student is doing well. This is the grade I will assign them. It has no other purpose, so you do not get to see your exam to review it. Can you see your lower score? I actually don't think that you can, but I'm not 100% sure on that. I want to say that you could see... oh, you know what it will do? You can't because of how I have it set. So, no. I guess the answer would be no to that. Because you'll click on both attempts, and both times it should say the instructor is grading this assignment, or you have completed the assignment. Please wait for the instructor to release scores, or something like that. So, your scores are in the gradebook. This is the teal deer version. Your scores are in the gradebook. You do not get to see how you did other than your score. I do not release the answers. Overall, people did quite good. That said, units 9 through 16, I think, are the harder units in the class. I guess I should say hardest, to use proper grammar. Unit 9 here, we're actually going to start by doing the easiest thing you're going to do in this class. And then we'll work on something else. We're going to do Unit 9 this week. Unit 10, maybe if we get time, but Units 9 and 10 are related. And they're all about bonding. So we've talked about matter, like what it is. We've talked about atoms, how they're made up. Now what we're going to do is we're going to talk about how we bond things together. The first examples that we're going to look at are ionic compounds, such as like table salt. So if you have table salt or any other ionic compound, ionic meaning it uses ions, it follows a specific sort of rules and behaviors. And we're going to talk about that in this section. Oh, I got to actually click on this in order for it to go. Okay. So we're going to define a chemical bond as any attraction between two atoms. Now, those atoms do not necessarily have to be neutral as a result. So the word atom is a little bit misleading in this context, in the sense that I could instead say ions. That's a more complete statement there, but for now, we're only going to look at individual entities. Later on, when we talk about polyatomic ions, we're going to see that, oh, I can have a bunch of atoms that all act as one big ion, and then that will be attracted to something that has an opposite charge to it. And that is also true, but for now, we're going to stick with just single entities. All right. Now, in chemistry, we pretty much rely upon one fundamental force and one fundamental force only, and that is the electrostatic force. Otherwise known as charge. Everything in chemistry relies around charge. And charge is a very simple concept that we discussed earlier. Opposite charges attract, and like charges repel. And everything in chemistry behaves on this notion. Now, we get a lot of interesting behavior because there is a very large range of charge of distribution that's available. And you might think, well, that's odd. There's like 3 things here. Isn't that it? And it turns out, not quite. Later on, what we're going to learn is that you can have partial charges. So you can have part of a positive or part of a negative based on how electrons behave. So it's not that we only have a third of an electron. It's just that we have an electron that spends a third of its time in this side of the molecule or something like that. And it behaves on the grand scheme of things like a third of an electron or something like that. We're going to talk about that in 161 when we talk about polarity. But for the beginning, we're going to only look at how electrons are involved in our interactions between matter A and matter B. Typically, that's going to be, either the electron is attracted to the nucleus of the atom it's attached to, or it's attracted to the nucleus of some other atom, and then interesting behavior occurs. Now, the type of bond that we use depends on how the electrons behave. In the first example here, ionic bonds, I have 2 atoms, and if this is my electron right here, I would pass the electron from one entity to the other, and in doing so, I create entities that now have charges. So if I remove the electron from A, it becomes positive, and if I remove the electron from A to give it to B, B then becomes negative. And now that these are oppositely charged, they would attract one another. And so that's the ionic bond. And I'm going to show you a picture of that in just a second, but it basically looks like what I just drew. Now, the covalent bond involves sharing electrons between atoms in the sense that if I have A, which has a nucleus that is positively charged atoms in there, and B has a nucleus as well, if I have my electrons for each atom, I can put some of those electrons in the space between them because these electrons will be attracted to both nuclei and thus hold the atoms together. So this electron is also attracted to this nuclei, and this one is attracted to this one too. And I realize this picture is not great. So let me do my charges here in black. And so we can put electrons in a specific spot to share them between 2 atoms, but they don't explicitly leave the parent atom that they are attached to. All right, Unit 9 is going to be ionic bonding. Ionic bonding is more detailed and simpler, so we're going to talk about that in this class to a greater extent. Covalent bonding is more complicated and requires some knowledge of quantum mechanics. We're going to leave most of that to 161, but we're going to go over a little bit of it in this class. All right. Now, this is a topic that we don't really talk about in this course, and we're sort of going to hand wave over it. But on the screen, you can see here that I have my electrons on different layers. And we talked a little bit about this in Chapter 8, where we said the period number is how many rows of electrons, or rings of electrons, there are around an atom. Now, electrons do not live on constrained rings. They live in regions of space called the electron cloud. But we use these diagrams as a sort of model to say, okay, my electrons in fluorine, I have the first layer, which is about this big. And then I have the second layer, which is about this big. And so I have electrons that live in layer 1, and I have electrons that live in layer 2. So in layer 1, there are 2 electrons. And then in layer 2, For fluorine, there are 7 electrons, for a total of 9. And you can see this behavior go on across, or as we go down the periodic table. So as I go from fluorine to chlorine to bromine to iodine, I add in a layer 3, and then I add in a layer 4, and then I add in a layer 5, and so on and so forth. Every time you add in a period, you add in an extra layer. Now, you also add other electrons in various places. So, for instance, layer 3 can hold up to 18 electrons, you can see. This is all very, very confusing and strange for you right now because, like, how do you get these numbers? Why are there only 2? And the reason that I'm going to use is that if you look at the periodic table, you can see that in the first period there are only 2 elements. In the second period there are 8 elements. In the third period, weird shit happens, and we'll talk about that in 161. But it's more or less trying to mimic the periodic table and where the electrons go. Sorry, drinking my water there. So, okay, electrons live in layers. That's cool, I guess. What does that mean for us? Well, if I have an atom, I don't have a cursor. Where's my... Oh, I'm writing in orange, and I can't see that. I have this teeny tiny dot. There we go. That's a little better. So here's atom A, and I have atom B. And atoms A and B have lots of electrons in them. Now, if these were going to bonk into each other, which electrons would see and encounter each other? Would they be the electrons in layer 1? Or would they be the electrons in layer 2? Assuming that both A and B were fluorine or something like that. Which electrons would see and contact each other? Layer 1 or layer 2? What do you think? I'm just going to chug more water while you think about it. Right, very good. It's layer 2, obviously, because they're the ones on the outside, yeah? So, the external electrons, particularly the ones in these regions that I'm drawing a little scribble through, the outer electrons these will participate in bonding. Whereas, oops, that's the wrong button. Whereas the inner electrons they're hidden from the view of the outside. You could think of this as like the layers on an onion. Each layer conceals the layers beneath it. Although instead of concealing the layers beneath it using actual, like, onion cells, we're instead concealing them with charge. Remember, electrons repel each other. So the outer electrons repel the inner electrons away from the outside and towards the nucleus. We're going to assign some terms to these. So inner electrons, which would be anything that is not the outermost layer, we're going to call these core electrons, because they live in the core. Down here, we're going to call these electrons valence electrons. Valence electrons are the outermost electrons, and they're going to be the important electrons. Was that a Shrek reference? I haven't ever actually seen Shrek. Not the entirety, I should say. Like, I know what Shrek is. And I've seen bits and pieces of it, but I've never seen the entire movie. So, sure? I don't know. Alright, so valence electrons are the outer electrons. So if I asked you, highlight the valence electrons on your atom or molecule, you would say, oh, okay, I'm going to just highlight the outermost electrons. And there they are. There's my valence electrons on iodine there. Ogres are like onions. That does sound like a Shrek quote, actually, given what I know. All right, so valence electrons are the outermost electrons on the atom. Now, because valence electrons are the only ones that participate in bonding, they're going to be the only electrons that we care about. And it turns out that there is a very convenient way to count valence electrons. First, we've already talked about the number of layers. So, for example, in bromine here, there are 1, 2, 3, 4 layers. We're going to refer to the layers as what are called shells, because this is just a quantum mechanical term. Shells of electrons. And the number of shells is equal to whatever period is on the periodic table for that element. This is written in blue, but I'm going to highlight it anyway. So, for instance, bromine has 4 shells, because I drew 4 lines through 4 different rings there. And so I would say it has electrons in valence shell 4. Iodine over there has valence shell 5. Fluorine has valence shell 2. And how do you get this information? It's just what period it is in. So which row of the periodic table you are in. That's all you have to look at, is which period. Now, the number of valence electrons is going to be equal to whichever group you're looking at. So you'll notice that all of these elements are in group 17. And the number of valence electrons on the outside is equal to the group number, but only for group A elements. And so what that means is on your periodic table, this is groups 1, 2, and 13 through 18. And so we'll write this down. And to know the number of valence electrons, you look at the ones digit. Ones digit equals number of valence electrons. So again, the row or your period tells you which layer your electrons are on in the valence shell. And the column or group tells you how many there are. Okay? So this is why we cared about the periodic table coordinate sort of system in Unit 8. We wanted to describe periods and groups so that we could do this. We can now count electrons and know roughly what layer from the nucleus all the electrons are on. All right, so let's grab a periodic table. So go to P-table. I'll put the link in here for you if you need it. So there's P-table. And what I want you to do, I'm going to give you 2 minutes to think about this and do this. I want you to tell me which valence shell and how many valence electrons are on phosphorus. So say valence shell X and then comma Y electrons or whatever, where you replace X and Y with the correct number. I'm going to hit mute. I'll go get the periodic table website ready, and then we'll look at these answers in 2 minutes. All right, one more minute. We'll go over the answer. All right, so you see on the periodic table here for phosphorus. So here it is right there. Hopefully this will stay selected if I do that. Well, I could do this, and you can see it over here. So you can see the 285 there on the side. Now, that is the electronic structure of phosphorus. There's a ring of electrons that says 2, or that has 2, and then has 8, and then has 5. And so the 5, the one at the bottom, is actually the number of valence electrons you want, because those are the ones that are on the outside. And so how do you come across that number? Well, phosphorus is in period 3. So it would be valence shell 3, which means the third shell is the valence shell. And then we would say, well, it's in group 15, which you can't see because I'm writing behind the periodic table here. And the ones digit tells us how many valence electrons there are. So there are 5 valence electrons. That's why we do this practice, so that you can see it in action. So phosphorus has a third layer valence shell, so valence shell 3, and has 5 valence electrons in that shell. All right, now what I want you to do is I want you to do the same thing. I want you to do this with oxygen, except not just O, but O minus. So this is not a typo. Make sure that you include this negative charge here, because it's going to change your result. So look at the periodic table. I'll even highlight oxygen for you. And do the same thing. Tell me what the valence shell number and the number of electrons is in O minus. All right, one more minute. We'll go over the answers. We'll just move this down here. You don't need to see my face. All right, so what period is oxygen in, whether or not it's oxygen with a charge or just neutral? Well, it's in row 2, right? So period 2. So it is valence shell 2. Okay, that's easy enough. Now, how many valence electrons does it have? Well, it is group 16. And if we use the ones digit, it should have 6 valence electrons, right? But that's for neutral oxygen. I have this charge. And that charge represents 1 extra electron, doesn't it? So instead of 6 valence electrons, we actually have 7 in O minus. So if you have just O, it would be valence shell 2 with 6 valence electrons. But O minus has 7 valence electrons because making it charged means we're changing the number of electrons, because that's what an ion is, right? Remember unit 7. So very good if you saw that. All right. Now this one you're going to have to think a little bit about. Let me clear my text here. How many valence shells and electrons are in the valence shell of calcium? Here's where calcium is. And what I want to do is I want to make it plus 2. So think about what its valence shell is. How many valence electrons it has, and then make it plus 2, and tell me what happens. Type your answer in the chat. I'm going to give you a second to think about this one, because this one's much more complicated. All right, one more minute. We'll go over the answers. All right. So in order to do this one, we're gonna first get rid of this picture. This here. I'm gonna draw my calcium here. So here's my calcium nucleus, and I've got my 1, 2, 3, 4 shells here, and then on shell 4 I have 2 electrons. So here's an electron, and here's an electron. Oops, for some reason the first electron has vanished. Not sure why that happened. All right, so you can see here on my picture, and also because it is in period 4, so this is period 4, that we're in valence shell 4. And because it's in group 2, there are 2 valence electrons. However, that's neutral calcium. I want calcium with a +2 charge. How do I make something have a positive charge? I take away its electrons, right? So I need to remove 2 electrons. So if I do that with my eraser tool, what happens? So I go boop, boop. Oops. Notice what happened there, conveniently. That actually wasn't intentional, but it worked out. If there's no electrons in the layer, we don't draw it, right? Why would we have a layer 4 with 0 electrons in it? Because there's nothing there, yeah? So we don't count that as the valence layer anymore. This decreases, and this becomes the next layer, which would presumably be full, right? Well, what would a full layer be? It'd be whatever the previous element had at the very end of the periodic table, which would be argon. So there should be 8 valence electrons in there. Now, the other way that you can do this is if I pull this picture back, and we're going to do this real quick. So you could see here, and I'm going to write this next to it. So you could see the number that corresponds to each layer of electrons. Well, if I remove 2, that's these 2, right? So what's the next valence shell? It's the next one down, valence shell 3. How many valence electrons are there? 8. So that's how you read those numbers on the electronic structure. So I could click any one of these that I wanted to. So for instance, if I wanted to look at, say, nitrogen here, this is nitrogen's electronic structure. And if I said, okay, what's the number of valence electrons? We'd say it's valence shell 2 because there's 2 numbers there. And that 5 is how many valence electrons there are. Well, if I then said, okay, I want you to actually consider N3 minus, well, the 3 minus means 3 more electrons. So you just add 3 electrons to what you got. So if this says 2, 5, and I wanted to add 3 electrons to it, there you go. So you can use these electronic structure diagrams on p-table. That's why they're there, to tell you the number of valence electrons and as well as the shell number. But if you don't have them, you can use the coordinates. You can just say, oh, it's in period 2, so it means it has 2 shells, valence shell 2. It's in group 5, or group 15, sorry, has 5 valence electrons. Stuff like that. I keep clicking on that. Okay. So now what I'm going to do is I'm going to give you a bunch of these and have you do the same thing. All right. So there you go. I have a bunch of atoms and a bunch of ions, and I want you to tell me the valence shell number and the number of valence electrons in each atom or ion. Be careful, make sure that you don't neglect the charges, especially if you are running on 240p, which is like what, cell phone resolution? Not even modern day cell phone. I would say that that's like Nokia resolution. So yeah, go ahead and try these. Type your answers in the chat. We'll go over the results in just a second. 2 more minutes and we'll go over the answers. All right, let's go over these answers here. So I need this. All right, so we'll put this over here. And then what we'll do is we'll go here. If I can find it, is this it? Yeah. All right, so we'll just put this right here. And then I will click on whatever element we're looking at. All right, so for this first one here, for arsenic, you can see the electronic structure there. Oh, I need to see where I can draw. There we go. Okay. All right, so for arsenic here, we can see that it's in period 4. Which means that it has valence shell 4. And again, you can tell that because there are 4 numbers on the electronic structure there, 2, 8, 18, and 5. What group is it in? Well, it's in group 15. What's the ones digit? We use that, so there are 5 valence electrons. And there are no charges on arsenic, so it's just as it is. That bottom number on arsenic there, the 5 in that column of 4 numbers there, that's the valence shell. The bottommost one is always the valence shell because it's going from inside to outside, from top to bottom. All right, so let's look at boron now. Where is boron? There it is. And we'll just scroll this guy off the screen. So we got boron, and it's got period 2. So it's valence shell 2. I'm just going to abbreviate it like that for save time. And because it's in group 13, that means the number of valence electrons would be the 1s digit, or 3 valence electrons. All right. Next, we have carbon, which is just next door. So for carbon, we've got also in period 2, which means that it's a valence shell 2. And it's in group 14. So it has 4 valence electrons. Oops. Hold on. Underline the wrong thing. There you go. That's what I wanted to underline. And then finally for fluorine, is that fluorine or fluorine minus? I can't tell. It is fluorine minus. I'm glad I checked. So first let's get fluorine on the screen there. So we want F minus, so we'll include that minus there. So first of all, it's in period 2. So that's valence shell 2. I don't know why I wrote it all the way out, but I did. And then it's in group 17. So we use the 1s digit, 7 valence electrons. But then I have to worry about this minus sign. Remember that the minus is an extra electron because electrons are negatively charged, so this becomes 8. All right, now I gotta hit clear on the screen here. Am I selecting this one? I did, okay. We'll look at barium, which is down there. Barium has a ton of electrons. And what are we doing to it? We are 3 minusing it. Okay. Is that a 3 minus? I gotta check. I can't see. Yeah, it is a 3 minus. Okay. All right, so what do we got? This is in period 6. So that means it's valence shell 6. And then it's in group 2, which means 2 valence electrons. But then we're going to 3 minus it. What happens when you give 3 electron, or when you have a charge of 3 minus? That's 3 extra electrons. So this becomes 3 more. There you go. Now, it turns out for this one, I actually chose a bad example. For our purposes, this is fine. This is what we want it to do. There is a little bit more that goes on behind the scenes here, which we'll talk about in 161. Oh, I didn't mean to scroll it down that far, actually. Potassium here. So for potassium, and we want to K plus this. So this is period 4, which is valence shell 4. And then it's in group 1. So it has 1 valence electron. But then I want to plus it, which means remove an electron. So what that means is this becomes 0. Well, you can't have 0, right? That means that this becomes 3, and we go down to the next layer, which you can see it says 8. So the answer would be 8 valence electrons. And then finally, for xenon, we'll just click xenon there. Nothing super exciting happening with xenon here. This is just regular old xenon, period 5. So it has valence shell 5. And it's group 18. We use the ones digit again, 8 valence electrons. All right. So hopefully you've noticed that by now the valence shell seems to have an upper limit of 8. You can never have more than 8 in the valence shell. You can have more than 8 electrons total. You can see there that there are 2 shells of 18. But those only fill past 8 when they're no longer the valence shell because reasons. And we'll get into those reasons in 161. So 8 is the maximum on the valence shell. If you go down to 0 for some reason, the previous layer becomes the valence shell, which will then have 8 in it. And we're going to look at this number 8 in a little bit more detail in the next section, which we're going to do after the break. So let me get the timer going. It's going to yell at me, hey, do you want to update this? No, for the 90th time. And we'll get the Metroid music going for our break. See you in a bit. Oops, sorry, I was reading something that somebody sent me from my online class that I have to take. Oh, let's do that first. There we go. Hi, everybody, welcome back. So now that we know how to count valence electrons, what we're going to do is this is the actual easiest thing in the game. The previous thing wasn't the easiest thing. So if you're thinking like, man, Wested was so easy and I'm here making mistakes over and over, that's totally okay. Because we do that exercise on the previous slide that I just had here. I do this for that reason, because counting valence electrons starts off pretty straightforward, but then you start adding the pluses and minuses into it, and it's like, oh man, I got to remember all this stuff. And as you get into the habit of it, it will get easier. So keep practicing that, quizzing yourself with how many valence electrons does this thing have? How does a positive charge affect that? How does a negative charge affect that? And of course, remember that electrons are negative, so a lot of the things that we do, they're going to feel backwards, right? Oh, I have a negative sign. That means I've added an electron. Even though negative means I should be subtracting, but you're adding negative things, okay? So be careful with how you are assessing the situation of what does the charge mean, okay? From the perspective of electrons are negative, and then work from there. If you have to sit down and say, okay, electrons are negative, here's what I do, every single time, then cool. Do that, because it will lead you to the right answer. All right, so what does this information do for us? How do we use the number of valence electrons in a constructive way that will help us for basically what we're going to do on Tuesday? And that is we make a picture of it. And this guy has already done that. This is G.N. Lewis. And you can tell he's important because he has a black and white photograph of himself. Ooh. We don't do that anymore. That's because no scientist today is important. No, I'm just kidding. There are plenty of important scientists today. But what G.N. Lewis did was he did a lot of study with bonding. And he devised this sort of cube-shaped representation that I'm going to try and draw here. Just real quick. So if this is my cube, and I got to put a back vertice there too. Then he said, okay, well, in my cube, there are 8 vertices. And he thought that these were going to be positions that electrons could be. And so his goal was to fill all these vertices, which I'll just call slots, with valence electrons. And if he could do that, then what he would observe is a bonded ionic compound. In other words, what he wanted to do is he wanted to have 2 elements that combined had 8 valence electrons, because they would fill all the slots. Now, we don't use this cubic notation anymore. What we instead do is we do something like this. Here's my sodium. Sodium has 1 valence electron, so I'll draw a dot. Calcium has 2 valence electrons, so I'll draw 2 dots, and so on. And so this is known as the Lewis symbol. And drawing a Lewis symbol is very straightforward. The first thing you do is draw the symbol, so Na, Ca, Li, Cl, O, C, whatever. And then you draw dots around the sides of the symbol, 1 dot per electron, in the valence shell. We don't care about any of the core electrons, remember. We're only going to draw valence electrons. Now, the last step only applies to ions. If you have an ion, add square brackets to it. You do want to indicate the charge. So, for example, if I had calcium, I would draw this. But if I had calcium minus, where I had a 3rd electron, I had to include the square brackets and the charge on it. That's just convention. That's just something that we do as tradition or something like that. This is what chemists like to do. All right. So I'm going to show you the visual example for sodium here. Sodium has this as its atomic symbol. Straightforward enough. Draw a dot for each valence electron. Sodium is in group 1. It has one valence electron. There, you draw its dot. It's not an ion, so you skip step 3, and then you're done. So if you can do what we did in the previous section, which is count valence electrons, you're going to do great on this, because drawing a picture is just, oh, okay, I'm going to draw dots for each valence electron. Here's oxygen. I want you to try and draw the valence symbol for oxygen. So look up oxygen on the periodic table. Find out how many valence electrons it has. And then draw the symbol, drawing some dots in. Now, I'll give you a hint. Put an electron on each side of the 4 sides before you start pairing them together. And we'll talk about why that is in a second. All right, one more minute to finish your diagram. I realize that this is virtually impossible for you to draw on the screen. All right, so hopefully here's what you did to draw the Lewis symbol for oxygen. So first step, you got to write its symbol. Well, it's O, just write an O. And then what you're going to do is you're going to draw a dot for each valence electron. If you looked at the periodic table, you should see that O is in group 16. So that means it has 6 valence electrons. We're going to put a dot for each side. Now, the convention is that you are going to put one dot on each side like this. And then you start pairing them until you're done. There you go. Now, does it matter where the unpaired electrons are? Turns out that the answer is no, because all we care about is that there are the same number of pairs and unpairs, regardless of how you draw the structure. So if I drew this, that's also correct, because I have 2 paired and 2 unpaired. If I were to draw, say, this, also correct. It doesn't really matter. There's a reason for that, and it's because we're trying to draw a 2D representation of something that exists in 3 dimensions. And in 3D, these would all be symmetrical. They'd all be the same thing. You just spin it around in some orientation. Now, what would not be okay? So these are all okay. What's an example of not okay? That would be something like this, where you have a whole side that's empty. In this case, you do not have the correct number of paireds and unpaireds, and so this one's not okay. So again, spread out your electrons as much as you can, and the reason that we're doing this, the reason that you do one on each side first, is because, remember, electrons repel each other, right? So they're going to take up as much space as possible. So take up one of each side and then pair them because you have to. All right. And again, it's not an ion, so we're going to skip step 3 for this example. All right. I want you to draw the Lewis structures for all of those ions that you just did before the break. So I made you draw out write out all of the valence shell and valence electron counts, which presumably you still have. Now you can quickly draw the Lewis structures because you know how many valence electrons there are. So go ahead and do that. Draw the dots around each of your symbols. You don't have to try and import them into the chat because, again, I realize you can't import a picture. So just tell me that when you are done. So I'll know, and we'll continue once I have a few dones in the chat. Okay, see you in a bit. All right, I see a few people are done. We'll go 2 more minutes, and then we'll go over the answers together. All right, let's go over the answers. So what I'm going to do over here is I'm going to write the valence electrons. I'm going to write the count of how many there should be in this spot. I'm going to write this for K+, and you'll see why in a second here. All right, so for arsenic, you would do something that looks like this. 1, 2, 3, 4. And you can pair the fifth one wherever you want to. I'm going to pick over here. There you go. So that's what you should have for arsenic. That's its Lewis structure. Or Lewis symbol, I should say. For boron, I have 3 valence electrons. I'm going to put 3 valence electrons. There you go. 1, 2, 3. Now, which 3 could you pick? You could have the blank in any position you want to. Again, it doesn't matter. As long as you have 3 that are unpaired and a blank. For carbon, there's really only one way you can do this because there are just enough sides for the number of valence electrons and you're all set. All right, so there's the first 3. Easy as arsenic BC, I guess. I don't know. All right, next we have fluorine. Now, fluorine normally has 7, but I made it a minus. I gave it an extra electron, so now it has 8 valence electrons. So we're going to put 8 dots around here. There you go. And because it's an ion, you got to do your square brackets and put a charge in the corner. Oop, what did I do? I accidentally clicked on the next slide. I was trying to neaten this up because it looked kind of ugly. There you go. All right. Next we got barium. What do you do with a dead chemist? You bury him. All right, here's barium. Barium has 2 valence electrons normally, but we've given it a 3 minus charge, so we're going to add 3 additional electrons. There you go. This is also an ion, so I'm going to do this. There you go. All right, last example before we get to xenon here, I guess. So second to last example, I don't know. We got potassium. Normally potassium has 1 valence electron, but if I'm going to make it K+, I need to remove that valence electron. There you go. Now you might think, well, wait a second. I actually have 8 valence electrons. Should I draw them all? And the convention is that if you end up on 0, you just don't draw any for the Lewis symbol. And the reason for that has to do with going back to G.N. Lewis's diagram here. If I can get back to his journal here. If you have something with 0 and the other thing has 8, then you have 8 total, and you fill in all the pips on his diagram. And so we're sort of following in his model. So even though it seems weird that we would say, well, that's not what the valence shell actually is for my diagram, when we're drawing Lewis structures or things that have 0 valence electrons, we just leave them blank, with the understanding that the previous layer, which is not shown, is the valence layer. Okay, so just be mindful of that, because from going on forward, I'm going to treat anything that has 0 valence electrons in its picture as 0. Now, what if you had K2+? Now, if you do that, you no longer have 0/8. So what you would end up having would be something that looked like this. That would probably be the proper way to do that. We won't really draw valence shells for elements that have gone below 0, we'll say. Like, I'm not going to ask you to draw the Lewis symbol for K+5 or something like that, or Br-4 or something that pushes you through to the next shell. This is really the only circumstance where this comes up in terms of what we're going to draw for symbols. And the reason for that is because these are the stable ions that form, the ones that land on 0 or 8, as we're going to learn in the next section here. Finally, we got xenon. Xenon just has 8 valence electrons, so you just put 8 dots around it. And there you go, you're all set. All right, that's how we draw Lewis structures. Let me know if you have any questions. Now, this one's special, it turns out. Xenon is particularly stable, and we've kind of talked a little bit about this. Just briefly mentioned it anyway. What noble gases are. Noble gases are the elements on the very far right side of the periodic table. And it turns out that they don't react very much at all. They tend to be quite stable. For instance, if you try and react helium or neon with stuff, they don't. And this is why you can breathe neon or helium or argon relatively safely. If you breathe in helium, your voice gets really high. And if you breathe in argon or xenon or stuff like that, your voice goes like this. And that's entirely because of the density of those substances. But they don't react with your lungs. In fact, they just kind of go into your bloodstream and then come back out, and nothing happens to you at all, other than you displace oxygen and may suffocate. So it's not entirely safe to only breathe helium. Like, you do need oxygen, but the helium itself will not react with your body. And the reason for this is because these substances are stable. Now, that's a how description. That would be a scientific law. All these elements are stable. But why is that? And it turns out that it has to do with their electronic structure. Just like you said there, their valence shell is totally full. If you have 8 valence electrons, the ion that you have formed tends to be the most stable representation of that element. And this is called the octet rule. The octet rule says, hey, if I have 8 valence electrons, I am stable, whether I am an atom or an ion. If I don't have 8 valence electrons, I will try and do anything that is required to get to 8. Now, remember, just like we said on the previous slide, 0 is the same as 8, right? If I get 0, the next shell down becomes the valence shell and has 8. So this is why we've been doing all of this analysis of like, oh, well, why do we call it 0 or why do we call it 8? Because it satisfies the octet rule. And that's our goal here, is we want to satisfy the octet rule for all atoms that we can. So over here, if I go back to this slide right here, Xenon satisfies the octet rule because it has 8 valence electrons. Potassium as a plus ion also satisfies it, but the rest of these don't. And so what that means is these would be stable, but everything else would be unstable, and thus would react if given an opportunity by shuffling around its electrons such that it attains an octet. And so what we're going to do for the rest of the day is we're going to look at examples of us pushing electrons around such that we make octets. That's our goal. So let's look at oxygen, for example. We drew oxygen earlier. I want to make it stable. It needs 8 valence electrons. So what do I have to do? I have to do this to it, right? I have to add in 2 electrons. So what's the stable form of oxygen? If I add those 2 electrons in, this is the result. Now, because I added 2 electrons, I have to do that. And there's my square brackets. There you go. Very good. So the stable form of oxygen by itself, atomic oxygen, I should say, is that it collects 2 electrons from something and becomes O2 minus as an ion. Now, the oxygen you breathe is not O2 minus. The oxygen that you breathe is actually this. It's 2 oxygen atoms bonded together, which is not an ionic compound. It's actually a covalent compound. So just in case you're wondering, like, oh, this is the oxygen we breathe. It's not quite. This is the oxygen that you observe in ionic compounds, such as sodium oxide or something like that. Okay, so this is different. And we'll come back to that later. Let's look at calcium. Calcium wants to fulfill the octet rule. So what will we do? Well, if I add 6 electrons, 1, 2, 3, 4, 5, 6, there we go, I would achieve the octet rule, right? But that's so many electrons. Is there an easier way? Because we're not going to do that. We're not going to add 6 electrons. That's too many. Not if there's a faster way to get to an octet. Nature's lazy, right? Nature wants to take the path of least resistance. And of its 2 options, it can add 6 electrons, or I could just get rid of these 2. That's far easier, right? So that's what we're going to do. We're going to remove 2 electrons to get rid of that valence shell, and then the next shell down becomes the valence shell. And so we always choose the easier option for our Lewis structures. So there's always 2 options, right? You can always give electrons or you can always take away electrons. Do the option that requires the fewest steps. Now, what if they're both equal? What if you're on carbon and you can either add or remove 4? Turns out that's a special case that we'll talk about when we get there. And by when we get there, what I mean is 261, which is organic chemistry. If you're a biologist, you could take OChem. Congratulations. All right, so what's the takeaway message for calcium here? It is that what we observe is the easier of the 2 actions. It is easier to remove 2 electrons than it is to add 6 electrons, because 2 is a smaller number. If I said you have to lift 2 boxes of books up the stairs versus 6 boxes of books up the stairs, you would say, I would rather pick 2. It's easier, right? Think of moving electrons around as something that requires effort, which it does. It requires energy. We're going to do the thing that takes the least number of steps. So to summarize what we've talked about for the octet rule, you have two options. You can either gain or lose electrons. Your objective is to make an octet, and the option that requires the fewest electrons to be moved is the option that you should choose. Now, elements on the left side in groups 1, 2, and 13 tend to have few valence electrons. They have less than 4. So they give their electrons away. These are the metals. So metals tend to give electrons away. Non-metals, on the other hand, tend to have a whole bunch of valence electrons. They want to collect more of them because they're already close to an octet. So an element that has 6 valence electrons will want to collect 2. An element that has 7 will want to collect 1, and so on. And then we have the odd exception, which is group 4A. Group 4A is so weird that there's an entire year of chemistry about it. Carbon is in the middle, and carbon is sort of in the Goldilocks just right position. It could either gain electrons or lose electrons, and so what does it do? It does both and everything in between because carbon is crazy. And so that's called organic chemistry. And you'll learn about organic chemistry in Chem 261 in your second year of college. All right, so what I want you to do here is I want you to look at each of these ions here, draw the Lewis symbol of them, and then predict the ion that forms and draw its Lewis symbol here. So, for example, for chlorine, here's what I would do for chlorine. So, chlorine, I have 7 valence electrons. How do I make it have an octet? What would I do to it? Well, I would add an extra electron and do this. And so that's the ion that forms, Cl-. Okay? I want you to do that for all the other elements. You can do this exercise, how many protons and electrons does each ion have, if you want. I'm gonna skip that because it's sort of just busy work. Down at the bottom, what I want you to do is I want you to look at all of these things and say, okay, do these have octets? If they do have an octet, circle them. And if they don't have an octet, draw an X through them. Now, keep in mind, we want the stable octet. So if there are 2 ways to make an octet, and I chose the bad one because it takes more steps, draw an X through it. There is one of the atoms on there that happens, okay? Go ahead and do these. We'll go over them together in just a little bit, and then we'll call it a day. All right, we're going to run out of time here if I don't go over the answers quickly. So we're going to do that right now. So for barium here, I'll just write in blue. It's fine. Barium has 2 valence electrons. I want it to attain an octet, so if I get rid of those 2 electrons, 1, 2, this would be the ion that I form. And it would look like that. For nitrogen, nitrogen starts with 5 valence electrons because it's in group 15. We're going to make it have an octet by adding in 1, 2, 3 electrons, and that's the ion that would form. We do the same thing for sulfur. Sulfur has 6 valence electrons because it's in group 16. We'll make it an ion to fulfill the octet by adding 1, 2 electrons, and that's the ion that forms. We'll do the same thing for phosphorus. Phosphorus has 5 valence electrons because it's in group 15. We're going to add electrons to give it an octet. So 1, 2, 3 were added. So that's the ion that forms. And then rubidium has 1 valence electron because it's in group 1. To make it have an octet, we're going to get rid of its 1 electron. We'll give it away. So that's what I have, and that's the ion that it forms. All right, last bit that we have to do is we have to circle any ions that should form and X out the ones that don't. So for aluminum, if I draw aluminum's Lewis structure, this is what aluminum looks like. What would its octet be? Well, I'd get rid of those 3 electrons and I get +3, so this is valid. What about selenium? Selenium has 6 valence electrons normally. If I want an octet, I would add 2 more, which would make it 2-, so that's also valid. What about bromine? Bromine has 7 valence electrons. So I should add an electron to make it an octet, which would be Br-. Oh, this is Br+, though. This is the opposite of what I want to do. This is not the ion that forms. Now, you could do this backwards, too. You could draw a picture of what you see here and see if it matches up. But then you end up in a situation. This is the tricky one that we'll get to. For calcium, calcium has 2 valence electrons. I got to get rid of those to make it 2+, so this is valid. But for phosphorus, phosphorus starts with 5. Oops, you can't see that one. 5 valence electrons. And in order to get to an octet, I have to add 3 more, don't I? So this should be P3- and not 5+. Now, by the same exercise, you can check that arsenic with a 3- is correct, but cesium with a - is incorrect. So those are the answers, because we're out of time here, unfortunately. But double check your answers with that, and ask me any questions that you have in the chat or on Discord. The chat's going to disappear in a minute here. So, but yeah, hit me up on Discord if you have any questions, or send me an email. I'm happy to answer those questions. So when we come back, what we're going to do is we're going to use these Lewis symbols that we drew for regular elements and then ions to predict what ionic compounds we can put together, because we're going to just start matching charges now. Once I have got octets, I then just put the charges that result together and attract them. What are the valence electrons for transition metals? They're beyond the scope of this class, unfortunately. Now, that's actually what I did my degree in, which is inorganic and transition metal chemistry. So I know a lot about it, but for the purposes of this class, we're going to ignore valence electrons and just go straight to the charge, which will be the subject of tomorrow's lecture. So we won't do Lewis symbols for transition metals because they don't follow the octet rule. They instead follow what's called the 18 electron rule, which is why you saw all those 18s when I had the... let's see if I still have this captured here. I think I closed it, and it's fine that I just don't put that up there. But that's where all those 18s come from that you saw earlier in the lecture. All right, I do want to thank everybody for coming out to the lecture. Make sure that you get quiz number 4 in if you haven't done it already. And, oh, there's another question. Let me put this back real quick here. So phosphorus is 3 valence shells. If you remove the outer shell and the inner one is 8, that would be correct. So if you remove the outer shell for phosphorus, we'll go over here to show that. Oh, I didn't actually click over here. So for phosphorus, real quick, here's what you're starting with. I'm going to draw 2 copies of it. So one thing that you could do would be remove 5. Or you could add 3. But this is more steps than this one. So this is what we do because it's fewer steps. Now, you get an octet going the other direction, but it's more steps, so it's not the one that we observe. Yeah, that's the trick there. So keep in mind, you got to watch out for that, because I will choose things that really look like they should be an octet, but it turns out that the alternative is faster. Because again, nature is lazy, and it wants the most energy-efficient option. All right, yeah, that's all I have. So make sure you get, what's it called? Get the quiz in by Tuesday. We're going to do lab number 3 on Wednesday, and I'll work on grading this week. See you tomorrow.